right. Thanks so much to the organizers for inviting me and the audience for coming. Now, you know, I would never accuse the organizers of making a mistake. I was thinking about what to do for this conference. It, you know, just made me aware of how little I know about W-algebras. But I do know one thing that I think is important about finite W-algebras, which I'm going to try to tell you because I think more people should know about it. The finite W-algebras in type A have this very interesting description. They're the Coulomb branches of certain quiver gauge theories. So kind of my intent in this talk is to tell you what that means and why you might care about it. And there is hope for BCD types, but you know, sort of, it's a little unclear. Things are much more complicated. But I don't think this is one of these things where there's sort of nothing interesting going on in BCD types, but I can make much better statements about type A. All right, so first thing I'd better tell you, what's Coulomb branch? So these were mentioned earlier in a few other talks, but not in much detail, and I want to actually tell you a little bit more about them. So there are some objects out there that physicists are interested in, and you don't need to worry about what they are. They're called 3D n=4 supersymmetric quantum field theories. If you know what those are, congrats. Don't worry about it. The important thing to know is if I start with a symplectic representation of a complex reductive group, there is one of these theories attached to it. And one of the most popular ways to build theories, so physicists would say, oh, the theory has this field content, right? So kind of the idea of quantum mechanics, or one of the ideas of quantum mechanics, is you have some average over histories. You think about all the ways that things could have happened, and you think about how probable each one of those is. And if you want to know what probably happened, you take some average over all of those correctly weighted. So for these, the notion of a history is a map of a 3-manifold into the symplectic reduction of V by G. All right. So attached to these, you know, these are big, complicated gadgets. I won't try to explain in any more detail than that what they are, but there are two concrete things that come out of them, which are two affine algebraic varieties. So the first of these is what's called the Higgs branch. So that's just the symplectic reduction. And here I mean the affine variety that I get by symplectic reduction. Of course, I could also think about GIT quotients, for example. And then there's the Coulomb branch. So the Coulomb branch, well, it's a little more complicated. We'll talk about it in a moment. I'll just mention here, since I'll say the words a few more times, there's a notion that these 3D theories should come in dual pairs. And so there should be some symmetry on these field theories. And one of the things that should happen is the Higgs and Coulomb branches should swap places. So when I take the dual of a theory, the Higgs branch of that theory becomes the Coulomb branch of the other theory, and vice versa. So on some level, looking at one theory and looking at the Higgs branch and the Coulomb branch, they're somehow supposed to be dual to each other.
Can I ask a question? So
Yes, of course.
what does the n=4, what does the n refer to actually?
So what the n=4 means is that your quantum field theory, so one of the things people often look for in a quantum field theory is that it has symmetries. So a natural kind of symmetry it might have is, for example, the Poincare group, or actually, you know, I'm going to rotate to Euclidean signature. So I would have an action of the isometries of Rn on my theory. So the special orthogonal group and translations. And so what the n=4 means is into that group, I also add in some odd elements. So that's the even part of a supergroup, which is part of the symmetries of the theory. And the n=4 tells me what supergroup it is. The odd part is the sum of 4 copies of the spinor representation of SO3. So the real significance to that n=4 is because n is equal to 4, this theory has two what are called topological twists. So there's a way of taking this theory, which you should think of a quantum field theory as like an algebra, where you can insert operators at different points, but the multiplication depends in some very complicated way on where they are. But often, there's a way of kind of cutting out part of the theory, which is taking the cohomology for a differential that comes from this superalgebra. So we've been talking so much about odd nilpotent elements. That's what I'm using. I'm taking the super Lie algebra. I'm looking at an odd nilpotent guy, and looking at using that as a differential. And so, for example, sometimes I'll get a theory where all the correlation functions, where I'm in 2 dimensions, and all the correlation functions are holomorphic in position. Certain kinds of twists give you that. That's a VOA, right? There'll be other twists that make things topological. So the significance of n equals 4 is that it's the least amount of supersymmetry you can have in dimension 3 and get a topological twist.
Okay, thank you.
If you go through the Lie theory, to cook up a topological twist, you need a 2-dimensional isometric, not isometric, what's the word I'm looking for here? Not Lagrangian, but, sorry? Isotropic, yeah. I don't know. Okay, yeah, I'm getting old. I was having trouble coming up with that. I need a 2-dimensional isotropic subspace of C to the script n. So n needs to be at least 4. And in C4, there are 2 different kinds of isotropic subspaces. There are 2 orbits of those under SO4, which correspond to the fact that SO4 is a product of 2 SL2 factors up to covers. All right, and so the Higgs and Coulomb branch come from those 2 types of 2-dimensional subspaces. And so the symmetry, it's supposed to swap the 2 factors, and so it swaps the Higgs and Coulomb branches. All right, cool. So, like I said, the Higgs branch, that's a symplectic reduction. That's something that hopefully all of you have seen somewhere in some context in your life. In fact, we've seen it earlier in the conference. But the Coulomb branch is much weirder. And for a long time, we were in the situation where Higgs branches, we were like, oh yeah, Higgs branches, we understand those. That's something really sort of concrete and easy for mathematicians to understand. And the Coulomb branch, well, the physicists would get a lot more shifty when you asked them about those. And they would say, well, okay, the classical one is I take the torus of my group, the complexified group, because physicists prefer compact groups. I take the cotangent bundle of that, and I mod out by the Weyl group. And then you would say, well, wait, that doesn't depend on the representation. And the physicist would say, oh, well, there's some quantum corrections. This isn't really right. That's only the classical answer. And then you would say, okay, well, what do the quantum corrections do? And they would say, well, they kind of change the metric, but then something else changes. And so, up until about 2015, it was very hard to get any kind of answer for what these were. But luckily, around that time, Raberman, Finkelberg, and Nakajima actually gave us a precise answer for how to add in these corrections. And then suddenly, maybe not everyone agrees with me, but I realized that Coulomb branches are actually much easier than Higgs branches. And that I had been a sucker for all these years trying to work with Higgs branches when they're much harder. All right, so what are Coulomb branches? I might regret this, but I felt like I should kind of go through the definition. So what these are based on is thinking about the geometry of bundles on disks and punctured disks. Don't let this scare you too much because things are actually fairly concrete. So I have these 2 spaces, which I interpret as the moduli spaces of principal G bundles together within a section of the associated bundle for my representation on the disk and the punctured disk. Now that sounds very fancy, but what does that mean? That means, well, on the disk or the punctured disk, I choose a trivialization of my bundle. And so the sections of the trivial bundle on the disk is Taylor series in N. The sections of the trivial bundle, the associated N bundle on the punctured disk is Laurent series in N. And then I have to remember, oh, I chose a trivialization. So I have to then mod out by the symmetry group that changes trivialization. So on the disk, that's Taylor series in the group. On the puncture disk, that's Laurent series in the group. And so I look at these quotients, which I could also think of as maps of the disk or the punctured disk into this stacky quotient of the representation by the group. So somewhere in the physics, there are maps into these symplectic quotients, and they kind of manifest here as looking at these spaces of bundles. All right. And the thing I really want to look at is the fiber product of two copies of the disk along the guys for the punctured disk. So the way I should think about this is I have two disks, and then I sort of look at the space away from the origin in these guys, and I glue them together everywhere except for the origin. So we often call this a raviolo. So I start with two sheets of pasta, and I stick the sheets of pasta together around the edges. As you know, that's very hard, but we can do it. But there's still a little bit of filling in the middle that remembers the difference between the two sheets of pasta. All right, so if you've done any Springer theory, then you know the thing we should do is look at the homology of this fiber product, and that will be a nice algebra that you can run lots of fun geometric representation theory games with. And there's a physics reason to consider this particular fiber product, but just in general, like when you have an interesting map, look at the fiber product of the thing with itself and think about the geometry of that. So this has a product. In terms of ravioli, the way to think about this product is this fiber product, right? That's two ravioli that got stuck together while you were cooking. And there are three maps, which are peel off the left one, peel off the right one, or mix the fillings and make one big raviolo. So you pull back by the maps that pull off the left and the right, and you push forward by the map that mixes the fillings. It's true. All right. You can also look at this picture with the cylinders and think about stacking cylinders, but that would be less tasty. All right. So this homology has an algebra structure, and you can see that it's commutative. This requires a little bit of work to do formally, but basically when the ravioli are stuck together, you could very carefully stick your hand in and rotate the two fillings. And because you have room to do that, roughly because pi 2 is commutative, I end up with a commutative algebra structure. And of course, if I have a commutative algebra, I should take the spectrum of it. And that spectrum is what we call the Coulomb range. All right, great. So there's going to be an important variation on this I want. So this is a nice geometric space that I understand. I get lots of things that I like. We'll see that the Slotowee slice is an example of one of these. But there's sort of an extra thing I can do. If I look at the normalizer of G in GLN, you can think of this as like automorphisms of the representation N that commute with G. That guy, mod G, actually acts on this whole space. And then there's one extra thing, which is I can rotate my ravioli. So there's an extra loop C star action, or you could say S1, it's the same topologically, acting on this space. So I could also take homology, not just normal homology, but homology equivariantly for this group. And then I would get a kind of deformed algebra, right? When I do equivariant homology for a space, my kind of baseline expectation is every kind of basis vector in homology now gives me a copy of the equivariant cohomology ring of a point, assuming you're equivariantly formal, and I promise you this is equivariantly formal. So I get a deformation of my algebra, but it's now non-commutative because I'm using this rotation action, and I can't swap the two fillings in a way that's invariant under rotation. All right. But that's actually kind of cool because taking the limit as I send the equivariant parameter to 0 now gives a Poisson structure. and that makes M into, well, again, oh no, this is actually a theorem now. It makes M into a symplectic singularity. Sadly, Gwyn isn't here to do a victory lap for this, but he proved about a year ago that you actually do get symplectic singularities out of this, this construction.
Can I ask a question?
Mm-hmm.
So your H here doesn't need to be connected.
My H here doesn't need to be connected. That is true. Now, in practice, usually I will make it connected. I mean, since I'm looking at equivariant homology and characteristic 0, I don't think it actually changes anything.
Yeah. But this way, wouldn't this change the zero fiber when you're taking lines?
Well, anyways, I can just take the connected component. All right, any other questions? Cool. All right, so the only case I'm going to talk about today is what's called a quiver gauge theory. So this means I take a quiver. I should probably draw a picture of a quiver like this, right? And we've talked about quiver variety, so I think you guys should be comfortable with this. I put vector spaces on all the nodes. I sum over HOMs along all the edges, and I'm doing things framedly. So I also, excuse me, have some extra guys here, which I'll always draw as red. So I have W's here, right, and I have V's here, and I'm always looking at HOM along edges. So this part of the representation comes from the black stuff. This part of the representation comes from the red stuff.
But should I think of it just as a framed quiver, or is
Yes, this is just a frame quiver. So the Higgs branch of this theory, probably should have said this, sorry, is a Nakajima quiver variety. Right? So we already are interested in this representation in group, and so it's a very natural question to ask, well, what's the Coulomb branch like? I'll mention this sort of crazy story about moduli spaces of, maps of this curve into the Stacky quotient. In this case, you can think about, well, what is n? So this is with Laurent series, and this is with Taylor series. It's just the moduli space of quiver representation with coefficients that are Taylor series or Laurent series, right? So as discussed, I think, in Martina's talk, right, if you want this space of quiver representations, again, you choose a basis in your vector spaces, you have actual matrices, but then you have to account for the fact that you chose a basis, and so you have to look at the basis change things. And if you do that with Laurent series, you have to look at GLN with Laurent series coefficients. If you do it with Taylor series, you have to look at GLN with Taylor series coefficients. All right. And then you can think of this BFN space as choosing a quiver representation over Laurent series and choosing two lattices inside it. Again, up to kind of the moduli space of all of those things. All right. Any questions?
So how you get these two invariant lattices?
Well, right, it's a fiber product, right? So the map from math SFY to OiScript Y, right, is I take a quiver representation with Taylor series coefficients, and then I forget that they were Taylor series and think that they could have been Laurent series. Well, what's kind of picking a pre-image? It's starting with something with Laurent series coefficients, and then choosing a basis where you get Taylor series coefficients. All right. So, given the theme of this conference, there's one connection with quiver gauge theories, which is kind of obviously important, and I suspect many people in this room know, which is you can write a Slodovy slice in type A as a type A quiver variety. And I don't want to get dragged down into the combinatorics, but there are some combinatorial formulas for what you want to do. You start with the Jordan type of your nilpotent. It spits out a dimension vector and, well, two-dimension vectors. You look at the Nakajima quiver variety with those data, and you get the Slodovy slice. Great. But there's supposed to be this 3D mirror symmetry. So things that are Higgs branches, you should also be able to write as Coulomb branches. Now I should say, right, we aren't talking about the most general theories. We're talking about gauge theories with linear matter content. There are lots and lots and lots of other 3D theories out there. So on kind of abstract grounds, there's some dual, but there's no reason that that should be a theory we have any way of accessing. But, you know, Witten and Hanani actually showed us how to do this about 30 years ago. So, luckily, we actually do know what to do. Yes?
So by Slow-Dovey slice, you mean the intersection of the Slow-Dovey slice with the nilpotent cone in this case, or the Slow-Dovey slice?
Well, I will deal with this here. So, depending on what I mean, I could mean both of those. Like, kind of both of them have interpretations in this world. All right. So, there's also a Coulomb branch interpretation. This one I will stay a little longer on the combinatorial data involved. So, I take an AN Dinkin diagram. My W is very simple. My W is just D, which is going to be the overall dimension of the space that my nilpotent is acting on. And then the way I get my V is I take the parts of my Jordan type, I put them in increasing order, and it is important that I put them in increasing order because for Nakajima quiver varieties, you want dominant weights. So this is the way to make sure you get a dominant weight. And then I look at the V, which is take the smallest part, take the sum of the two smallest parts, take the sum of the three smallest parts, etc. So in terms of these pictures that people like, right, I would put D0 here, and then D0 plus D1 here, etc. And then the last thing would be a red box with a D in it. All right, so this is the quiver gauge theory whose Higgs branch is T star of a partial flag variety. So this is sort of part of this mirror symmetry story. Nilpotent orbits should be 3D mirror dual through Slow-Dovey slices. So the affine quiver variety attached to this guy is a nilpotent orbit. It's the one attached to lambda transpose. And so it's not surprising that we get the Slow-Dovey slice here. Okay, so using the notation I had before, if I don't put in any extra equivariance, I get a commutative algebra, and that is functions on the Slow-Dovey slice intersected with the nil cone. I put in my extra invariance, and what I get is the finite W algebra now with the big center. So the big center comes from the equivariant cohomology of a point for my H, which in this case is PGLD, right? So I have GLD acting here, but the scalar matrices inside it actually lie in the gauge group acting on the other nodes. So the quotient of the normalizer by G is PGLD. And indeed, the equivariant cohomology of a point for PGLD is the same as the center of the universal enveloping algebra for SLN. All right, so the family going from the nil cone to all of the Lie algebra is throwing in the equivariance for H. So if I did H but no C star, I would get the functions on the whole Slow-Dovey slice in the full Lie algebra. And then when I turn on my H, I get the W algebra.
And here M is the Coulomb branch for this quiver.
Yes. Yes, it's spec of A. Spec of the equivariant homology of that fiber product.
A with H equal to 0.
All right. And I should maybe mention the credit here. So the BK, the proof of this uses Brundtland and Kleshov's isomorphism of the W algebra to the quotient of a shifted Yangian. It's really the shifted Yangian that sort of shows up in this Coulomb branch picture. And then Braverman, Finkelberg, Kamnitzer, Kodera, Nakajima, myself, and Alex Weeks all wrote down together the fact that that this Slotowski slice matches up with the shifted Yangian. What had happened there was, I think there were 3 groups of us who had separately figured this out. This is sort of something where as soon as this definition of Coulomb branches existed, it was obvious this had to be true. And it's just a matter of kind of writing out the proof.
You said that you wrote down that the shifted Yangian matches up with the Slotowski slice. That's what
Well, no, that's
you
up.
meant to say that you
Brendan
wrote down that the
Kleshev.
Coulomb branch
Oh,
identifies.
I'm sorry. Yes, that the Coulomb branch
Yangian.
matches the shifted Yangian. Yes, I'm sorry. That's what I meant. So that's what happened in the appendix written by that obscene number of authors. And you can see I tried to write down the initials by memory and I screwed it up. So, all right. So why do we care about this? What does this buy us? It does get us some interesting stuff. So for example, for just any group in any representation, the algebra A has a maximal commutative subalgebra, which I'll call gamma. And by equivariant formality, which is very easy to check, the algebra A is always free as a left module or a right module over this guy gamma. And there's a very explicit basis. Basically, the basis is indexed by dominant co-weights of G, and each one of those contributes a copy of the equivariant homology of the corresponding flag variety. So for example, the trivial co-weight contributes this subalgebra gamma itself. And all the other ones contribute sort of basis vectors over gamma, which are called dressed monopole operators.
When you say that it's easy to check, what do you do? You see that you have no homology, no degree, so how do you check
Well-
equivariant formality?
So you know that fact for the affine Grossmanian. Okay, well, this BFN space is a kind of over every Schubert variety in the affine Grossmanian. It's an infinite rank vector bundle.
Okay, thanks.
So once you know it for the affine Grossmanian, it's very easy to transfer that over. And you know, right, if you know the homology of the affine Grossmanian, this is exactly sort of the size that it has. So each one of these contributions is coming from the G of O orbit of T to the nu in the affine Grossmanian.
What did you say that the 2 correspond to again?
So this co-weight, right, in the affine Grossmanian, the orbits of G of O are indexed by dominant co-weights. Right? And the homology of the whole space breaks up as a sum of kind of contributions from those co-weights.
I see. And sorry, what is it? So this is H equals. This is the H equal to 1 you're talking about here when you say.
This is sort of this is all with H equals 0, but it's sort of true for all variations of things.
Yeah, maximal commutative subalgebra, right? Don't you need A to be non-commutative for that?
Oh, yeah, sorry, you're right.
And then why is it? And then why is it maximal?
Well, I mean, I can prove it, but you're right that part is only true if H is equal to 1. Now, it's still true if H is equal to 0 that you get that you have this subalgebra and you're a free module over it, but you're right, it's not maximal commutative in that case.
Maximal Poisson commutative.
Yes, it is. All right. So for example, in the W-algebra, this is what's called the Gelfand-Cetlin subalgebra. So the W-algebra has a bunch of sub-W-algebras coming from, look at the first part, look at the first 2 parts, look at the first 3 parts. You might be more familiar with this for U of SLN itself, where you look at SL1, SL2, SL3, SL4. This is just a generalization of that for the W-algebra. And exactly as in U of SLN, I look at the centers of these guys. They're all polynomial rings, and they're all algebraically independent from each other. They give me a big commutative subalgebra. And exactly what's happening here, right, is my group is a big product of GLNs, and the equivariant cohomology for that GLN contributes the center of one of these W-algebras. And I'll just mention, you know, one of the things that sort of has definitely happened in this theory is we periodically find out, like, oh, that was something you didn't know? Oh, it's really easy to see from this perspective. So it had been a conjecture that the W-algebra would be free as a module over the subalgebra. As far as we know, it had never been confirmed. But from this Coulomb perspective, it's very easy to check geometrically. All right, another application, which I should thank Yvonne for talking about some of this stuff first. It allows us to define what I would call an analog of the Cherednik algebra for the W-algebra. So, right, the W-algebra, it's a quantization of a symplectic singularity. Another such quantization that's very popular is the spherical Cherednik algebra. The spherical Cherednik algebra sits inside the full Cherednik algebra. They're Morita equivalent for most parameters, but not for all of them. And the full Cherednik algebra behaves much better. It's always finite global dimension. It's sort of just generally nicer. So,
U?
sorry?
Who is U?
U, that's just the polynomials.
Okay.
All right, so there's a non-commutative algebra that I'll call R circle sub H, which contains an idempotent that gives me almost this scripty A, but not quite. There's this extension that often comes up with universal enveloping algebras where I have the center and I have to extend to all polynomials. So the sort of thing you should think about is when you look at universal differential operators on G mod B, you don't get the universal enveloping algebra, you get the extension of it where you tensor its center with functions on the torus. This is exactly the same kind of thing. All right. So, yeah, the W algebra sits inside here as a corner algebra for some idempotent. When I specialize all my parameters to 0, I get a non-commutative resolution of the Sloterdijk slice. And in fact, this guy shows up as the endomorphism algebra of a tilting generator on the resolved Sloterdijk slice. So Yvonne in his talk talked about this sort of special vector bundle living on T star G mod B. Well, in fact, any conic symplectic resolution has such a special vector bundle called a tilting generator. And I'm running a little low on time, but we'll talk a little bit. There's sort of a very complicated construction of them. But in this case, using the Coulomb branch machinery, you can write down a very concrete presentation of it. All right, so there's sort of general theorems, the most important of which are due to Coulomb, which tell you that such a thing must exist. But it's very hard to figure out what it is in general, but I will tell you. All right, are people ready? And suddenly I have to start doing some combinatorics. So the way I'm going to describe this algebra is in terms of certain kinds of diagrams. So remember I had some VI's, which were the dimension vector for my quiver. So I take a VI tuple of paths in the circle for each I. So that's just a map of the interval into the circle. And I'll usually draw these by drawing graphs on the cylinder, sort of layering them on top of each other and putting I's next to them to remember which VI tuple they came from. On these paths, I'm allowed to add dots at distinct points. And there's an n tuple of special elements. Oh, that should have been a d tuple, I'm sorry. A d tuple of special elements where I draw red lines, right? And this is at a particular point in S1, so when I draw the graph, it's a vertical line. All right. And all of this data is supposed to be generic. So there are no triple points between all these things. There are no tangencies, and dots never sit on crossings. All right, so the picture I get is something like this. Right? So each one of these red strands is one of my paths, and I'm drawing the graph of it. And I don't know, because I'm weird like that, I'm not drawing the graph on the side, I'm drawing it up and down. So I've swapped x and y from the usual way you draw graphs. And then there are dots at various points. And here I've drawn the graph on the cylinder. It's kind of hard to follow what's going on when you draw it on the cylinder. It usually works a little better to cut the cylinder down the side and draw it smoothed out. So I tried to draw the same picture two different ways. All right, are there any questions?
What did you say this was a graph of?
Well, so every one of these red strands is the graph of a function from the interval to S1. Right, another way to say that is it's not allowed to turn around. It's not allowed to have maxima or minima. That's sort of the main thing. All right. All right, and then I impose some local relations on these, which depend on the labels on strands and basically allow me to kind of go through the non-generic points. So the way you should think about all of these relations is they always look at one of the configurations I'm not allowing. So, for example, these correspond to a tangency, and looking at the two different ways of resolving a tangency. And I get some relationship between those. So this is resolving putting a dot on a crossing. This is resolving triple points. I'm not going to go through these in detail. If you've seen them before, they're the KLR relations. So what I'm drawing is sort of a cylindrical version of a KLR algebra. All right, and as I said, inside here there's a subring which looks like A, which comes from kind of looking at all the guys with the same label and pinching them together at the bottom, and pinching them together at the top, and putting them in a particular order. And I realize now I neglected to mention something. So as we discussed, there are these kind of two flavors of things. There's the deformed version, the undeformed version. And here I wrote the relations for the undeformed version. Let me not try to write the relations for the deformed version, but I'll just say, so the center of the W algebra comes from adding in dots on the red strands as well. The red strands sort of correspond to the center of the W algebra, and red strands on those sort of let you keep track of those guys. The quantization corresponds to adding in a relation where if a dot slides on a strand all the way around the cylinder, I add H to it. And H is sort of, all of this has some geometric meaning, and that has to do with when I move the dot around the cylinder, I'm actually changing the loop action on it. So the dots correspond to Euler classes of tautological line bundles, and it's like, oh, when I do that, I'm thinking of my tautological line bundle with a different loop equivariant structure.
What do you mean by adding H to it?
I mean that I replace a little, right, all of these relations are, when you see one side of the relation as a little part of your diagram, you can cut it out and replace it with the other side of the relation. So it's really like I kind of cut out a dot and replace it with a dot plus H bar times no dot, but the same strand there. And I'm happy to explain this. It's not that complicated, but I'm already pretty short on time. So I'll worry about that. That's something we can discuss later. So we've all learned that's a very important thing to say. Now you might say, wait, you've only talked about the Slotowee slice as an affine variety, but it has this resolution that's very important. So I'll just say, you can get that resolution in this language as well. So that's proj of some graded ring, and I can write down that graded ring by adding in rotations of the red strands around the cylinder. So basically, right, if I'm going to take the proj, I have to pick some ample line bundle, and choosing that ample line bundle sort of says, for every one of these strands, I'm going to decide a number of times it wraps around the cylinder. And so, like, the first power of my line bundle is going to be wrapping around that many times. The second power is going to be wrapping around twice as many times for each one of them. The third power is going to be wrapping around 3 times as many times. And a particular reason I like this is this operation lets me turn modules over this R circle into coherent sheaves. So to get a coherent sheaf, I need a module over the projective coordinate ring. So something where I can add these diagrams with rotations of the reds at the top. And I can do that by just saying, oh, I have a module over R0. I put those guys at the bottom. I then put on diagrams that start matching something in this module and then connect to the special idempotent at the top. And then I can put more things with the special idempotent, but red's going around on top of it. And that's what this means, right? This is diagrams from N, guys with J rotations on top of it, and then this special idempotent at the top, so functions in the Coulomb branch connect. All right, so this looks like kind of a strange functor, but it turns out it's actually a derived equivalence. So in particular, the module R0 itself gets sent to some coherent sheaf, which is a tilting generator. Okay. All right, again, maybe I'll just put this up, say a few words, and if you're interested, we can talk later. This is the tilting generator that comes out of the construction that Yvonne was talking about. So I think in characteristic P, I do a Frobenius constant quantization of the resolved Slotowee slice. So I get this non-commutative guy whose sections are the W algebra with a big center. I sheafify over the big center, I get an Azumaya algebra. That Azumaya algebra doesn't split, but again, this Coulomb branch picture gives me a very nice way of thinking about the splitting. I have this integrable system inside the non-commutative guy, and its intersection with the B center is also an integrable system there. So the way I split my Azumaya algebra is I look at a fiber of that integrable system inside the P center, and if I kind of follow everything through, that's saying that the Gelfand-Cetlin subalgebra in the non-commutative guy has eigenvalues in FP. It ends up being the Artin-Schreier map. So the guys in the P center having eigenvalue 0 means the guys in the non-commutative guy have eigenvalues in FP. And these pictures, I think of the P torsion points of the circle as the elements of FP. And I sort of understand what's going on as I put my dots at the eigenvalues of the integrable system. All right. So that's the trick. I think we'll leave any discussion of that for later. Whew, okay. So maybe the sort of takeaway point here is you have this kind of horrible construction in characteristic P that people kind of think of as like very, very hard to understand. But because of this Coulomb branch presentation, you can really get your hands on it and say exactly what you get and sort of see much more clearly some of this stuff about how uniform things are when you change P, right? So this definition works over Z, but I can reduce it mod P for all P. It's easy to see kind of what the bad P are. So it kind of makes this construction much more concrete. As with many things in this talk, it's a little bit of a solution in search of a problem. So if you have some problem with this stuff, let me know and maybe we can solve it. All right, in the remaining time I have left, I also want to say a little bit about the representation theory of finite W-algebras in characteristic 0, which you can get out of this sort of Coulomb branch picture. So there's a natural class of modules you can look at, which are the finitely generated modules where gamma acts locally finitely. So I probably should have said a finitely generated Z module. And you'll note here I'm specializing H bar equals 1. So I'm really looking at the finite W algebra and the scalar C that's modding out by a maximal ideal in the center. And just to simplify my life, I'm going to look at modules that are integral, so not just integer values of C, but integer values of that specialization for all of these sub-W algebras, right? So if I have this Gelfand-Cetlin module, right, I have this finite dimensional space, so I can do Jordan decomposition on it. I can look at the guys that are killed by powers of maximal ideals And I just always want maximal ideals that are indexed by integer values. Makes my life much easier. All right, cool. In particular, when I do that, that means I can think of a point in max spec as a conjugacy class of co-characters. All right. And if you want to understand these Gelfand-Sutherland modules, so for example, if you like category O for W-algebras, every object in category O is Gelfand-Sutherland. So this is some bigger version of category O. And includes category O for all Borels. If you want to understand one of these modules, well, one way to do that is to look at these sort of weight spaces, W gamma. So for each maximal ideal, I look at the stuff killed by powers of that maximal ideal, and then look at how natural transformations between these functors act on this. It turns out there's a very good way to understand this, which I should say is based on kind of ultimately work of Eric and Michaela about affine Springer theory, and has been expanded on by many people now. So I look at my gamma, there's a co-character that corresponds to it. So I can look at my original representation n, and I can look at the space that has weight greater than 0. And there's a vector bundle I can cook up from that guy, right? There's a Borel, I should say, right, this is conjugacy classes of co-characters, so I can assume that it's dominant. So that subspace is invariant under the Borel, and I can cook up the associated vector bundle on the flag variety, which now has a map down to n. Oh, and I should have changed this. That was supposed to be an n. All right. And as we discussed in geometric representation theory, when you have spaces like this, look at the homology of their fiber product. It's a good thing to do. And it turns out here, I missed a lot of things. I should have put a equivariant for G there. The equivariant homology of this fiber product for G is exactly the Hom spaces between these functors. So the geometry of this space, this fiber product, which now I have a product of flag varieties and I have a vector bundle that's kind of singular over G orbits, actually completely controls how these weight spaces interact. So for example, if n gamma and n gamma prime are equal, the weight spaces are naturally isomorphic. There's a natural transformation between the functors, which is an isomorphism between them. And so those weight spaces will be the same in every module in a canonical way. I should say natural way, because there are many natural isomorphisms between them. Okay, well then you might say, well, how am I supposed to think about all these co-characters and what's positive and what's negative? But it turns out there's a good accounting method for it, which is exactly what we did before, but on a line instead of a cylinder. So I take the not cylindrical, the linear KLR W algebra. It's almost exactly the same, except that I have maps from 0, 1 into R. So I get pictures like this instead of the ones on the cylinder. And again, the position of the points you should think of as the eigenvalues of elements in the Gelfand-Sutherland subalgebra. That's sort of the information you get here. All right, exact same relations, no difference. All right, so how do I connect these? Well, for my gamma, if I want to know what spaces are, which weight spaces are allowed or not allowed, well, I have to think about, okay, what are the weight spaces in this quiver representation space? They're all matrix coefficients in these quiver maps. And so I ask myself, when do I get positive or negative weight for all these matrix coefficients? Well, they connect one basis vector to another basis vector. So I look at the weight of one basis vector for one GLVI. I look at the weight of the other basis vector for GLVJ, and I look at which one is bigger. So the way I'm going to sort of do all my accounting is I'm going to look at my co-character. I'm going to look at the weights it has on c to the v1, c to the v2, c to the v3, etc. So this is an example where, so my d's, d0 equals 1, d1 equals 1, d2 equals 3. So it's the nilpotent 3, 1, 1. And so I'm going to have my v's are v1 equals 1, v2, it's the sum of the two smallest parts. So it's 2, and, oh, sorry. I forgot I was supposed to start at 0. No, I wasn't supposed to start at 0. I'm doing this right. Okay. And v3 is 5. It's the sum of the three smallest parts. All right, so I have a co-character into GL1, a co-character into GL2, and a co-character into GL5. And I look at the eigenvalues I get, and I just pay attention to how they're ordered on the real line. So I chose one particular example, 6, 1, 8. So for example here, right, 6 is between 1 and 8. So I should have two 2's and a 1 between them. And I picked minus 1, 2, 3, 10, 13. So I'm thinking of the co-character that C star maps in, and these are the exponents that I'm raising my element of C star to. And if I did this right, 1 is between minus 1 and 2. So the 2 should be between the first two 3's. 6 is between 3 and 10, as is 8. So 1 and 2 should be between the third and the fourth. So this is just a way of taking the sequence of numbers. I only care about which ones are bigger than other ones, so I just write them down on the number line. And there's no danger of getting confused about which 2 was which, right? Everything's up to conjugacy, so there isn't like an 8-1 that's different. So I don't have to keep track of like which 2 is which. All 2's are the same. All right, so this ordering of things gives me an idempotent in this algebra, where just all the strands are vertical. And it gives me sort of a top and a bottom I can choose. So what ends up happening is if I want to know the natural transformations from one functor to the other, they're just diagrams that are compatible with one weight space at the bottom and the other weight space at the top. So again, if the orders are the same, the weight spaces are isomorphic as functors. They're isomorphic in every module. But if they're different, well, every diagram gives you a map from one to the other. That's natural in modules. And in fact, if all the CIs are distinct, we get an equivalence of categories between modules over this ring R and the category of Gelfand-Settman modules for the W-algebra. So I should just mention, somehow there's very little serious study of this category as far as I can tell. There are a few papers about it. There's this paper of Futorny, Molev, and Ovsienko, but not too much else. In particular, I don't think anybody had any idea what the list of simple objects were. As far as I know, even for U of GLN, even for U of GL4, the list of simple modules had been completely open. That's my understanding of the situation. And for SL3, it was like a 100-page paper. There were a lot of pictures, so Yeah.
If we are interested in the smaller category of the finite dimensional module category, does this R module say obvious some new perspective?
Yes. So category O is I look at this algebra, and I set to 0 all diagrams where there's some horizontal slice where the first thing I encounter coming from the right is black. So basically, right, if I have some slice where the first thing I encounter from the right is black, that means if I look at the different eigenvalues I have, there's one from one of the VI's that's bigger than all the ones coming from the WI's. And since it only matters what order things come in, I can make that one for the VI as big as I want, and my object isn't in category O. So sort of the, you can think of category O. Yeah, anyways, we can talk about it later, but yes. Category O is a natural quotient of this guy, and finite dimensional modules is kill all the diagrams where you encounter something black coming from the right, and when you encounter something black first coming from the left. So yes, it's a very natural thing. Any other questions? So again, it's a little bit of a solution in search of a problem, right? I don't think too many people knew that they wanted to know the list of simple objects in this category, but luckily, now you all will. So I'll just mention there is sort of a nice combinatorial description of all the simples. So for each simple module, there's a sort of nice way of indexing it. You look at all the words where the idempotent corresponding to that word. So right, I would have a word like this, and then I would think of the idempotent where I have strands in that order. There's a unique lexicographically minimal word such that this product is non-zero. And it turns out, actually, for each such word, there's at most one simple where that's the lexicographically minimal. This is something you can check explicitly from the structure of the algebra. And then there's a precise characterization of what words appear as lex minimal. And they're what I call red good. So I have some sequence of I, Ks, and J, Ks, such that I take the word where I take I minus 1, ... down to J, and I concatenate those in some order. And I have a slightly strange combinatorial condition, which is the i's must be weakly increasing. And if two i's are the same and not equal to n plus 1, then the j's must be increasing. All right. I don't know what I think I meant order instead of orbit. But all right. So what I mean is, for all the words that start with something less than n plus 1, there's a distinguished order of them. There's only one order that they can come in. And for every pair of them, either the i's are different, and this rule tells me what order they should be in. And if the i's are the same, then the j's are different, and this rule tells me what order they should be in. Whereas the ones that start with n plus 1 could be in any order. All right, and indeed, these completely index the simple integral Gelfand-Cetlin modules over the W-algebra, where I've fixed the central character to be generic. So basically, it's not on one of the walls of the Weyl chambers, or not in a singular weight, I should say. And I just thought I would put an example here of kind of how this process works, right? So I have a word, and I sort of try to check if it's in this form of these words where things decrease and they come in the correct order. So for example, this guy is okay. I have a word that's just 1, a word that's just 2, and a word that's just 2. And my i's increased, so it's okay. And then words that are just 3. Here I have a word that's 1 and then 2. That's okay. That's W21. And then 2. And again, the i's weakly increased. The i's were 2 and 2. And the j's increased. There was 1 and then 2. Right? This is W21 and then W22. All right, and then I just have words that are all 3s. So I better include one bad example in here to illustrate what's going on. Here I have a word that's 2. Here I have a word that's 2, 1. They're in the wrong order. These guys are also okay, and what I'm emphasizing here is the ones with 3s can just come in any order. That's fine. For those of you who like category O, you can identify modules in category O because all the words that show up start with the last number, n plus 1. So for example here, this guy is not in category O. This is the only one which is in category O. And here I'm thinking about the category O that's bounded below. There's bounded above and bounded below. Is if you wanted the bounded above, you would do everything backwards. All right. Any questions?
But you said if ik is equal to ik plus 1,
Did I put the wrong? Yeah, that's right. So that happened here. J1 is smaller than J2, right? So this guy is okay. But here,
wait, so J1 is, so J is smaller than I?
yeah, and so this case is the I's are 2 and 2, the J's are 1 and 2,
Okay, so you go downwards.
right?
Okay.
Whereas this one is 2, 2, and then 2, 1, and that's bad. I mean, if you know about good words for universal enveloping algebras, the rules for things that don't start with the last element are the rules for good words. So like this issue about 2, 2, and 1, you should think about like the monomials in the universal enveloping algebra of SL3 for 2 E2s and 1 E1. And there's a linear relation between those. So if you want a basis, you have to say that 2 of those are good and 1 of those is bad. And this is exactly why 1 of those is bad. And then basically because the reg strands aren't allowed to move around and cross, you don't have that order condition on the reg strands. All right, I think I'm over time. So I won't say much here, but obviously it's a valid question. What about types B, C, and D? Yeah, since I'm over time, let me not try to say very much. There's this notion of orthosymplectic quiver varieties, where instead of having 2 nodes with labels on them and HOMs back and forth, that would be the symplectic representation, the cotangent space to HOM from one to the other. I instead alternate symplectic and orthogonal groups, and when 2 of them are adjacent, I tensor the natural representation for those. And that's a symplectic representation. The tensor product of a symplectic form and a symmetric form is symplectic. So I get a symplectic representation here, which I would love to apply the BFN construction to, but that would require writing it as T star of something, and obviously I can't do that. There is some hope. Thanks, Grubier. There is a generalization of the BFN construction. I didn't write down the names. It's Braverman, Finkelberg, Dillon, Travkin, and Raskin. Unfortunately, it's not clear what's going to happen when these are applied to orthosymplectic quivers. And it's both not clear because I haven't done it, and it's not clear because Nakajima gives some talks, but he hasn't written anything down yet. But we sort of know from some calculations done by Hanani and collaborators that some of these are not going to work. So we have kind of candidate choices for all special orbits, but there are some where you can just tell, like, you aren't getting a cone, so you definitely are not getting a Slotowee slice. Nakajima has given some talks about this stuff, so if he, gets less busy presidenting and gets to writing some papers, maybe we'll find out what happened, but maybe someone else will have to do it.